Hi everyone. In today's video, we're going to continue our discussion on carbonyl chemistry. We're now on the 14th episode of this particular sequence, and we are going to focus today on a major reaction called the aldol reaction. And so the goal for this particular video is that we would be able to predict the product, identify reagents and conditions, and propose reasonable mechanisms for this particular Aldol reaction. So in our conversation around Aldol reactions, the first we're going to look at is called an Aldol addition. But before we even delve into that, I think it's first important for us to remember this particular insight that when we are under basic conditions, your aldehydes and your ketones are always in equilibrium with their enolate form. So what do we mean by that? So that means that if you have an aldehyde in your flask and you're under basic conditions, then you're going to form some percentage of your aldehyde that will be converted into an enolate form. And then if you have a little bit of water in there, then you may actually be able to form the enol. But let's ignore the enol for a second. The key thing here is that you have your enolate and you have your aldehyde, and the enolate is formed by deprotonating the alpha position of your aldehyde. And so at equilibrium, both the aldehyde form and the enolate form actually are both present in the flask. And because of that, you can actually have reactivity between the aldehyde form and the enolate form. Remember that the enolate form is nucleophilic and the aldehyde form is electrophilic, and they're both in the same flask. And so your enolate can actually react with your aldehyde to form a compound called a beta-hydroxy aldehyde. So let's go over what that would look like. So here's your enolate, which by definition is a resonance stabilized anion. Well, your enolate can actually now act as a nucleophile and attack another aldehyde in the flask. So that's why I'm highlighting that in blue. And you can imagine because your enolate is nucleophilic at this carbon and your aldehyde is electrophilic at this carbonyl carbon, your enolate can attack your aldehyde, which should end up giving you a molecule that looks like this. That developed alkoxide can then get protonated by water in the flask to form this particular product. So let's break down this product to understand why we call it a beta-hydroxy aldehyde. So with respect to your carbonyl carbon, I have denoted the alpha and the beta position, and there's a hydroxy substituent on the beta position. And of course, the carbonyl carbon is actually within a functional group called an aldehyde. And so we call this a beta hydroxy aldehyde. And this is actually the aldol addition product. Okay, so we've basically extended the chain of your aldehyde by the exact same number of carbons in the fragments of the aldehyde using this aldol addition. Okay, so let's focus on this particular aldol addition reaction and let's think about equilibria. So when you're dealing with an aldehyde, so if it's an aldehyde specifically, just like what we talked about, that undergoes an aldol reaction, the equilibrium actually favors the aldol addition product, so the formation of that beta hydroxyaldehyde. And so let's say you have this particular molecule, this aldehyde right here, and you treat that under sodium hydroxide and in aqueous conditions. You can always have an aldol addition product. Recall that because you're under basic conditions, you will always have an equilibrium between the aldehyde form and its enolate form in which you deprotonate that alpha position. And so the way you can think about drawing and predicting the product of this particular aldol addition product is by taking your particular molecule. So note the alpha position that I have specified on our substrate. You can redraw your substrate on the right-hand side. And once again, note the alpha position on your substrate. Okay, so that is actually going to be the location, if you remember the mechanism we just talked about, in which the enolate is going to form and attack another molecule of your aldehyde in the flask. And so that connection point is right there. The aldehyde is going to be reduced to an alcohol. And then you can simply add on the carbon chain or the carbon fragment associated with the aldehyde on the left-hand side. And so one way you can do this is just count the number of carbons on that aldehyde chain and just make sure that you are following along when you add on the extra aldehyde to the aldehyde that became an enolate. Okay, so this would be your aldol addition product or your beta-hydroxy aldehyde. And so what we're saying is that at equilibrium, the major species is actually the beta-hydroxy aldehyde, and then the minor species would be the remaining aldehydes in the solution. Okay, and so this reaction, the equilibrium decay Q here is actually going to be greater than 1, leading you to your beta-hydroxy aldehyde. Okay, so let's once again look at the mechanism of this reaction. So if you notice, I started my substrate by actually redrawing it in the same direction as the way I have it in my product. And the reason why I do it this way is that you would see that the mechanism is going to make a little bit more sense, given that you're going to deprotonate this particular alpha position on this particular chain. And to explicitly drawing out one of those alpha protons so that I can actually be poison it for deprotonation is also going to be pretty helpful. And so under basic conditions, your proton transfer reaction deprotonating that particular aldehyde will lead you to your enolate, which of course, as we know, is resonance stabilized. So your enolate now is your good nucleophile, and remember that you're going to attack an electrophile at that alpha position. And so now with another aldehyde in the flask, you can imagine now you have your aldehyde here, which is electrophilic at that position, and then your enolate, which is nucleophilic at this position. As always, the lone pair drops down from the oxygen, which would then foster the nucleophilic attack of our aldehyde carbonyl, and then the CO pi bond break, and then the electrons move towards the oxygen. And so following your arrows, you should see that you would end up with a molecule that looks like this, which can of course be protonated by water, which then gets you to your beta-hydroxy aldehyde. Okay? So the mechanism should be pretty straightforward. If you think about this, you're just forming your enolate. Once again, we've seen this before, and we've seen how the enolate carbon can act as a nucleophile. The only difference now is that we've changed the electrophile to now be another molecule of your aldehyde. You form the deprotonated beta-hydroxyaldehyde, and then you protonate that with water, and you get to the particular aldol addition product. Okay, so on the other hand, though, if you use a ketone and then you subject your ketone to aldol reactions, the equilibrium actually favors the ketone side over the aldol addition product. So for example, say you have your cyclohexanone and then you treat that with sodium hydroxide, that's your basic conditions in aqueous solutions. Well, we know that just like your aldehyde, your ketone has an alpha proton in which you can then engage in an aldol reaction. And so once again, to predict the product of this reaction, what I would do is redraw that substrate, put a marker at that alpha position, which is going to be your connection point between the enolate of this substrate and then the ketone. And so then you make your connection, you throw in your hydroxy group, and then finish up that particular carbon fragment with the exact same carbon fragment you had in your original substrate, which means that we would want to incorporate a cyclohexane ring right at that carbon connection point. Okay, so we see here that we have a ketone, and at the beta position, we have a hydroxy group. And so this aldol addition product is called a beta-hydroxy ketone. So very similar to your beta-hydroxy aldehyde, just now we're dealing with a ketone. So what we're saying is that at equilibrium, the minor species is actually your aldol addition product, and the major species is actually your ketone itself. And that you can kind of see just by visually looking at this molecule that your your aldol addition product is actually pretty sterically encumbered. And so because of that, you can imagine the equilibrium will want to free up that steric strain that is incurred in your aldol addition products. The reverse of this is called a retro-Aldol reaction, where your aldol addition product is actually being released to reform your aldehyde or ketone in the flask. So let's take this particular aldol addition product and then look at the mechanism for the retro-Aldol reaction, so going back. So starting with our beta-hydroxy ketone, under basic conditions, you can imagine that your hydroxy group can get deprotonated to form the alkoxide form of this. Okay, so now this is going to be a little bit of a weird situation that we actually kind of seen before, but we're going to bring this back here as a new trend happening with these types of alpha carbon chemistry. So we have a tetrahedral carbon at the beta position, in which you have an electron-dense group on it, which would suggest that this tetrahedral carbon is going to want to collapse. But while there is no really like an apparent good leaving group, given that all of these are carbon, however, this group is not just a regular carbon, it's actually an enolate, which means that the carbonyl that could actually be formed when you engage in a loss of a leaving group here is actually going to be stabilized through resonance, making it more likely to be able to leave this tetrahedral center. And so in order to disengage, you can imagine that your tetrahedral center can collapse in such a way that would actually remove your enolate from that particular tetrahedral center to form your enolate and then kick off one of your ketones from this particular aldol addition product. And once again, the reason why this is a reasonable enough mechanism is that the fragment you're removing now is actually a resonance stabilized carbon. And so that's why it's more likely in this case to actually be kicked off your tetrahedral center. In any case, though, your alpha position can once again get protonated by a water in the flask to then reform your ketone, which would then conclude your retro-Aldol reaction. Okay, so this actual direction is much more likely when you're dealing with a beta-hydroxy ketone in your flask. The reverse or the retro-Aldol reaction is a more likely reaction than the actual aldol addition reaction. So now let's look at aldol condensation reactions. And this can actually be thought of as almost like after you do your aldol addition, other things can actually happen. One of which is that you can actually eliminate water from your aldol addition product, so your beta-hydroxy ketone or your beta-hydroxy aldehyde. And you can go through an elimination that would actually get you to a particular molecule, which we call an alpha beta unsaturated aldehyde or an alpha beta unsaturated ketone. We call these alpha beta unsaturated aldehydes and ketones your aldol condensation products. So once again, this is taking your aldol addition product and subjecting it to high temperatures, and essentially you can do an elimination from there. So we've already formed these two different types of aldol addition products, one of which is your beta-hydroxy aldehyde, and one of these is the beta-hydroxy ketones from the previous scenes. So under the same reagents, but now we heat up the system, both of these can actually form alpha-beta unsaturated compounds. And so what you can think about here is look at that alpha and the beta position on your aldehyde and your ketone, which I have now highlighted and denoted by alpha and beta, and think about an elimination that removes an OH group as well as the proton at the alpha position to then form a pi bond between the alpha and the beta positions. And so here would be the product of these two different reactions. So on the top, now this is an alpha beta pi bond. That's what we call an alpha beta unsaturated aldehyde. And here we have an alpha beta unsaturated ketone. It's important to note that regardless of if you started from a beta hydroxyaldehyde or a beta hydroxy ketone, this reaction is actually pretty thermodynamically favored under elevated temperatures. And the driving force here is that in both of these systems, you can note that now you've created conjugated pi systems in this reaction, which would then further stabilize the products that you've actually formed. And so even, for example, your formation of your beta hydroxy ketone being disfavored, if you heat up your system, you would then convert pretty readily to an alpha beta unsaturated ketone, which is actually indeed favored in your reaction. Okay, so let's look closely at what an aldol condensation can look like. So you have your cyclohexanone, which is a ketone, and you are under sodium hydroxide and aqueous conditions, which is suggesting that this is going to go through an aldol addition reaction. And so you might imagine that maybe what you would see first as your product should look like this, right? Which gets you to your beta hydroxy ketone or your aldol addition product. But you then realize, okay, we also have heat in this system, which means that your aldol addition product can actually undergo elimination to form your alpha beta unsaturated ketone. And so the next reaction in this sequence would be the elimination of your H2O from this particular molecule to then form your alpha beta unsaturated ketone. Right? So we've actually basically seen each individual one of these in the previous scenes, but now putting it all together, you can see that an aldol condensation is really just an aldol addition plus an elimination at the very end. Which is to say that our mechanism can be separated into two parts. One is the aldol addition part, and then the other is your elimination part. So let's think about the mechanism of this reaction. So beginning with your ketone, your hydroxide can deprotonate the alpha position to form an enolate, which we know is resonance stabilized. But in any case, that can act as a nucleophile to then attack another ketone in the flask. To form the deprotonated form of your aldol addition product, which can then be protonated by water, and then get you to your beta hydroxy ketone. So we know all the way from here, this is really not favorable. So you're not going to get too much of your beta hydroxy ketone in the flask. But that being said, there will still be some of it. And so the beta hydroxy ketone can then undergo an elimination to form your alpha beta unsaturated ketone. And so now let's actually think about what that mechanism looks like. So we've actually seen a mechanism like this before in the past. This actually goes through what we call an E1CB mechanism. So it's an elimination that's unimolecular, but the CB actually stands for conjugate base, which means that an anion is actually being formed here, not a cation like a regular E1 reaction. So we've seen this before, but let's think about what this reaction will look like. So you have your beta hydroxy ketone, and at the alpha position, you do have an alpha proton. So of the many different things that can happen with this particular beta hydroxy ketone under basic conditions in this flask, one of them is that your hydroxide can actually deprotonate at alpha position, which gets you to this particular anion. And at the risk of sounding like a broken record player, the enolate is resonance stabilized, right? And so that kind of is your driving force for that particular proton transfer step. But in any case, now you can actually do what we call an elimination reaction here. So we've deprotonated this alpha position. We formed a conjugate base. Now we can kick off this hydroxide group through a loss of a leaving group step. So what I want you to do is follow my arrow pushing from the enolate oxygen to the displacement of that particular OH group. So your enolate oxygen lone pair can come back down, almost like it's about to reform its other resonance form, which would be the carbanion. But instead of doing that, it can directly go over one bond away to form a pi bond. And then that would then end up dislodging the OH group from your beta position and then form your alpha beta unsaturated ketone. Okay, so like we just mentioned, under um, elevated temperatures, pretty much all your aldol addition products are going to be converted into aldol condensation products. So you can think about this reaction as essentially a two-part reaction. One is the aldol addition and then the elimination. The key thing to note here, and remember that this has to be in the presence of heat. So heat is sort of the kicker right there. If you know heat is added, you know you're going to go from an aldol addition to an aldol condensation. So up to now, we've looked at aldol reactions in which a molecule like an aldehyde and ketone essentially reacts with itself, right? So you take the aldehyde or the ketone, you deprotonate it from the enolate, and then in that same flask, you're going to have the aldehyde and ketone in there, and then the aldehyde or the ketone in that flask can then act as an electrophile, and you form your aldol product. But what if we wanted to perform an aldol addition between two different compounds? So, for example, what if we decided that we're going to take this aldehyde and then we're going to try to do an aldol reaction with this other aldehyde? Okay, well, so what we're attempting to do is called a crust aldol reaction. Basically, it's an aldol reaction across two different compounds. But as you can probably see here, the big problem here is that both of these molecules, the one in blue and the one in red, both have alpha positions with alpha protons on there. And so under sodium hydroxide conditions, there are actually four different possible outcomes that can happen here. So one of them could be, okay, you have your red aldehyde acting as your enolate, so you deprotonate that alpha position, and then you attack your blue aldehyde. Okay, so that's a cross-aldol reaction. We say yay. But you can also have the case where your blue aldehyde becomes your enolate, so you deprotonate at that alpha position, and then it attacks this red aldehyde, and you form this other cross-aldol product. That's messy. You can also have the case where your blue aldehyde acts both as your nucleophile in its enolate form and an electrophile in its aldehyde form, and essentially you form a regular old aldol. So this is not your cross-aldol reaction anymore. And lastly, you can imagine, once again, now it's your red aldehyde acting both as your nucleophile and your electrophile, and now you have this other aldol product. And then you end up with a complete mess, right? This is a mess in your flask, right? Nobody ever wants to deal with four different products to try to separate and isolate and try to like characterize as well, right? So we don't want to do this, right? We want to figure out a way to perform cross-aldol reactions where we don't get a whole mess of products in our reaction, right? So let's try to figure out what that would look like. So there are two strategies you can use to try to do a cross-aldol reaction where you minimize the mess that happens in your products. So strategy number one is you can just make sure that one of your aldol coupling partners does not have any alpha protons. Because if it doesn't have any alpha protons, it can never act as your nucleophile. So one example of an aldol coupling partner that does not have any alpha protons is your formaldehyde. And so not only does it not have any alpha protons, it's also highly electrophilic. And so the major product here would basically come from the enolate of this particular aldehyde attacking the formaldehyde here. Note that you will still get some of your minor product where this longer chain aldehyde can act both as a nucleophile and the electrophile. So you will still get some of this, but the majority of your product should be the cross-aldol product because once again, you're dealing with a highly electrophilic formaldehyde. Another example of an aldehyde that has no alpha proton is your benzaldehyde. So you have your benzaldehyde right here, and you can once again react another aldehyde with this benzaldehyde. And because it has no alpha protons, it's never going to act as your nucleophile in the reaction. But and then under these conditions, you will form your beta-hydroxy aldehyde. But interestingly enough, this reaction or this product is really not isolatable, even if you use low temperatures here. And the real reason why is that if you actually consider what the condensation product looks like, so when you actually remove water from the particular aldol addition product, you end up with this highly conjugated system. So not only do you have an alpha beta unsaturated aldehyde, which is conjugated, this in itself is conjugated with the entire benzene ring. And so that's really stable, that this is really not going to form in any appreciable amount, even under mild temperatures. And so what we just do essentially to very quickly form this highly conjugated system, you take benzaldehyde with any other aldehyde in your flask, and then you treat it under aldol condensation conditions. So you just heat it up, and then you will just get to this particular product in pretty high yields. But of course, notice that this strategy, it's pretty limited in scope, right? So you're pretty much forced to only use formaldehyde or your benzaldehyde or some aldehyde that has no um, alpha protons, that's also relatively electrophilic as well. That's not very helpful. So we need another strategy as well that can help us increase the scope of our cross-Aldol reaction. So the second strategy, which is definitely more robust, is you do this step by step. So you actually separate out your synthesis into three distinct steps. The first is you take a particular aldehyde or ketone. So let's take this acetone, and you first treat it with lithium diisopropyl amide. So we know LDA is a pretty strong base that would deprotonate the alpha position on this particular ketone. When you're done with that step, then you treat your product with another aldehyde in a flask. Then you treat your product with another aldehyde. You react that all the way, and then you add water. So you're basically separating out your mechanistic steps into three distinct syntheses if you're really thinking about this. So in synthesis steps, the first one is you treat your carbonyl containing compound with LDA, which essentially forms your enolates, right? So that's your enolate in the flask. And you do this in a way that you don't actually react your enolate with its own like ketone or aldehyde in the flask. And so the way this is actually done from a synthesis point of view is that we actually start with a flask filled with LDA. So that's actually what you put in the flask first. And then you do essentially a titration. It's like a drop-wise addition of your ketone or your aldehyde into that flask that is filled with LDA. And the reason why is that you want to make sure that for every little drop of this ketone or aldehyde you put into this LDA, it all turns into your enolates. And you never really have an appreciable amount of the ketone or the aldehyde in the flask that would then react with your enolates in the flask as well. So you do this dropwise, 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 dropwise until you get to all of your enolate being formed with no ketone or aldehyde in the flask. And then in your next synthesis step, you then add your other aldehyde coupling partner into the flask, which would then react in one direction where your enolate attacks the aldehyde carbon, and that's really the only direction you're going to go, which would then form the deprotonated form of your aldol addition products. And then it's after that is formed completely, then you then neutralize or wash up your product with water, which would just serve to protonate that oxygen to form your beta-hydroxy ketone in this case. So note that the reason why we have the aldehyde in a separate synthesis step as your water is that you want to avoid protonating your enolates by any kind of proton source in this particular reaction. You want to keep your enolate as a good nucleophile that would actually attack your aldehyde in a nucleophilic attack to form this particular aldol addition product. Okay, so this is a pretty good strategy. It has pretty wide substrate scope. Notice that we can even mix and match. We can have a ketone start in at first, which is our enolate, and then we can then bring in an aldehyde, and we can still do this, right? And it would actually form your beta-hydroxy ketone without much fanfare because you don't have that much of a steric bulk at that particular tetrahedral center. Okay, so that's it, right? I'm hoping that you're able to start seeing how to predict the products of Aldol reactions, thinking about the way their connection points occur, And you can start identifying the reagents and conditions necessary for an aldol addition versus an aldol condensation versus a cross-aldol reaction. And then you can start to propose reasonable mechanisms for these different variations of Aldol reactions in your problem sets. Thanks so much for watching this video, and I will see you in class.